Hello. So we are ready for the third video on logarithms, the third and final video in this unit actually, where we're going to talk about change of base, and that's going to let us do some pretty important applications of the logarithm function. Okay, so the reason I have saved change of base for last is because I think these associated properties can be the most challenging for students. That's been true in my experience of teaching. So I'm going to take this a little bit slower, but it's actually fewer properties altogether. Okay, so let's go ahead and get started. So when we talk about change of base, we can talk about change of base both for exponential functions and for logarithmic functions. So we're actually going to do change of base for exponential functions first, and this one is actually, I think, a little bit easier. Okay. So what we're going to do is we're going to take an exponential function. Suppose that a population is modeled by the exponential function y equals 300 times 2 to the x. And what we're going to do is we're going to convert this function so that the base is e instead of 2. All right. Before we actually get started, why would we want to do this? So why would we want to convert the base? Okay. Well, different bases have different properties, kind of depending on what you're interested in. So base e is generally the most common base. Okay, we call base 10 the standard logarithm. That's kind of a misnomer. It's really base e that is more standard than base 10, unless you're an engineer. Base e has the best mathematical properties. Okay, we've talked about this before in the last unit. E to the x is the function where the slope is equal to the y value. So when you're doing things, especially when you're doing things related to rates of change, which you do a lot when you're looking at things like population, anything that's growing or decaying exponentially, then you're likely to want to convert it to base e because it's going to make those kinds of problems a lot easier. And that's especially true in calculus class next year. Why would you might want to convert something to base 10. Generally, you would do that if you wanted to estimate it by hand. And that's just because powers of 10 are the easiest to compute. Okay. In rare cases, you might want to do things like convert it to base 2 if you're kind of interested in it as like a function that doubles every so often. But I would really say that base e is the most common and very occasionally base 10. Okay, so how do we actually do this problem? So it's pretty simple, really, once you see that it's just about a substitution. Okay, so we start by taking 2 itself and putting that in base e. And the trick is to remember that composition of inverses cancel. So we can write 2 as e to the ln of 2. Okay, that seems like we're going backwards, right? Now you might be thinking like, okay, I'm used to maybe taking e to the ln of 2 and canceling that and get 2. This is seemingly making it worse by rewriting 2 as e to the ln of 2, but that's how we solve this problem. Okay, so once we have that, we can substitute that into our equation. So we get 300 times 2 to the x equals 300 times e to the ln of 2 to the x. Okay. The last step in this is to remember that when you have repeated exponents, like we have right here, that becomes multiplication. So I can rewrite that as e to the ln of 2 times x, where the exponent in this function is now a product, ln of 2 times x. And it is important to know that the x here is outside of the log. Some people don't always write this in parentheses, and I think that's a little bit dangerous. You really want to remember that x is outside. Otherwise, it would all just cancel and give 2x, but that's not what's happening. Okay, so that's for this particular problem. There's a general change of base formula, but it involves this exact trick that I just talked about. If I want to change from base A to base B, then what I do is I rewrite a as b to the log base b of a. And once I have that, then I just turn that repeated exponents into a product, and this is the formula I get. So when I ask me, how do I remember something like this? I just remember it as that substitution. I don't remember it as this very specific formula with these specific variables. And the variables are going to change their names all the time, so it's better to remember it as a process. Okay, so there's an important side effect that I have to point out because it's going to come up in an example problem later on. Because we can do this, because now we can change the base of exponential functions, we can rewrite any exponential function to have base e, meaning that any exponential function can be in the form y equals c times e to the rx. Okay, so the trade-off by making the base e is that now we have this extra number in front of x, okay, which in this case, this example problem was ln of 2. All right, now why would we want to do this? I mentioned that it would be good to do this because it makes calculus problems easier, problems to do with rates of change. And now I'm going to mention this fact from calculus, and I'm going to mention it because it's going to play a role in these example problems later on. I won't be able to prove this fact, but it is something that I think we have just enough calculus to be able to understand what it's saying. All right, so this function, c times e to the rx, has the property that for any point, the slope is equal to r times the y value. Okay, this should be familiar. Remember that in the last unit we said that exponential functions always have this property that the slope is a constant times the y value. But now when we write the function this way, we can know exactly what that constant is. That constant is this number in front of the x, the r in this. Okay, that's only true if we're using base e. So because of this fact, this property, r, this number, is often called the relative rate of growth per unit of time for this exponential function. Okay. The per unit of time bit is going to be a little bit strange. It depends on how you're measuring time, what unit your x variable is in, and we're going to see that in the example problem. In fact, all I want us to take away from this right now is that that's just what we're calling the r in this function. I'm going to interpret that in a couple slides. So I want you to have this in your notes, and I just want you to know that's what we call the r in this function. Awesome. Let's keep going. Okay, so we can change a base for an exponential function. We can also change a base for a logarithm. Okay, so in this case, suppose that we want to express the function log base 2 of x in terms of the function ln. Again, why would we want to do this? Because ln is a more convenient function when it comes to things like rates of change, just like e to the x is a more convenient function when we're talking about exponential functions. All right, so this is I think the property that's the easiest to get confused. It's the easiest to forget, and it's not an especially easy property to derive. I'm going to derive it in this slide. It doesn't take that long, but I don't expect you to remember the derivation. I just think that it's something that everybody should see once. I am going to, I'd be happy to take questions on this in class. And I wouldn't be surprised if you had questions coming from this derivation because it's just a little bit tricky. All right. So what we're going to do is we're going to start with the equation y equals log base 2 of x. We know, because of the definition, that we can turn that into the function 2 to the y equals x. So I'm actually going to be referring to both of these in this calculation that I'm going to do. Okay. So the hardest part of this calculation is the start. I'm going to start with the equation y times ln of 2 equals ln of 2 to the y. So that seems unmotivated right now, but that's just because it's going to lead somewhere interesting. It's okay if we don't know why yet. Why is this equation true? That we should know, because I'm using this rule that says that I can take an exponent inside a log and turn it into a coefficient outside the log. I'm doing that backwards a little bit, but you'll see why, because I'm going to make this into a nice equation. Okay, so first I just want to see, why is this first step true? The next two steps are about substitutions. I started with y equals log base 2 of x, so I'm going to substitute that in for the y that I see over here. So that's all I'm doing. Substituting y equals log base 2 of x. That's the only thing that's happened to the equation. In the next step, I'm making another substitution. I'm substituting 2 to the y equals x. Okay. But that's coming from this second equation up here, which is saying the same thing as the first one, right? So again, no problem, just a substitution. So in this process, I've turned this equation from something with just y's in it to something with just x's. Last step, I divide the ln of 2 to get it to the other side of the equation. That's just algebra, right? I'm just dividing both sides of an equation by the same thing. And now look at the last line, because I've actually solved the problem in this weird unmotivated way, right? I've taken log base 2 of x and I've rewritten it as ln of x divided by ln of 2. And that is the change of base formula. Okay. So there's a more general version of this where we're changing from any base to any other base. And here it is. Okay. If I want to change from base A to base B, then I want to set up this equation, log base A of x equals log base B of x divided by log base B of A. So it's really the same thing that I have here. It would have exactly the same derivation, just with more variables involved, and that's not necessarily good. So there's nothing different about this other than, in this case, A is 2 and B is E, right? So what's going on here, and how do you think about it? How can you remember something like this? Okay. So first, to kind of explain a little bit about what's going on, when you go from log base A to log base B, really all that's happening is you're dividing by a constant, and that constant is log base B of A. Okay, this is actually a graph transformation. When you divide a function by a constant, remember, that's what we call a vertical squash. Or maybe a vertical stretch if you're dividing by something that's less than 1. But in any case, it's just a vertical transformation. And that's actually the difference between the bases of logs. They're all vertical transformations of each other, or specifically vertical stretches and shrinks. Okay, how do you remember this? Because that's maybe the most important thing. We're going to be using this all the time, and we're not going to want to derive it every single time. So how do you remember it? The easiest way I found is to remember that, sure enough, I mean, the base A is going to become base E. So it's mostly about the order, whether you write it as x over A or A over x. And it's not too hard to remember if we look at the original thing and realize that in this original expression, the x is kind of above the A because the A is a base, so it's sitting down below, and the x is kind of above it. So that's what helps me remember that when I rewrite that, I want the x to be above and the A to be down below. Okay, that's the best way I've found to remember it anyways. Okay, so really those two properties that we had on these last two slides are the most important thing, and I'm just taking time to make sure that we're kind of comfortable with these. Let's do some applications. Okay, well, let's do one application and then I'll give you the homework problems. All right, so in this example, we have a bacteria culture. It's growing exponentially over time, according to this, and they're telling us what that relative growth rate is. Remember that that's the R from a couple slides ago. All right, so if there are 2,000 bacteria at the start of the experiment, how many hours does it take for the bacteria to reach 10,000? All right, so the first thing we want to do is we want to set up an exponential equation. They're telling us the growth rate, so that means we have to use E as our base. And then R is going to be this number 0.0462. And 2,000 is that initial value. Remember in the last unit, the coefficient in an exponential equation is what you're starting at. It's what you get when you set time to be 0. Okay. Let me say something before I actually finish this problem. Let me say something about units here, because this is a little weird, especially if you've never seen this in a science class. So this really is, I didn't make a mistake with this slash. This really is 0.0462 per hour. Okay. The confusion is 0.0462 what per hour, right? Well, that's best talked about as a percentage. Okay. So it's actually, the reason there's no units above the hour is because percentage doesn't have a unit. All right. Now 0.0462 is not a percentage, but if I turn it into a percentage by moving the decimal place over 2 places, then I get 4.62%. Okay. And that's exactly what this means. It's saying that the bacteria is growing at 4.62% per hour. Okay. So it's not an absolute growth rate. It's not saying that it has the same slope at all points, but it's saying that the slope as a percentage of the y value, which is the population, is a constant, and it's constantly 4.62%. Okay. I expect that we'll talk a little more about this in class because it's a weird thing to think about. The units here really are like inverse time, like over hours. Now that doesn't really affect how you solve the problem. It just affects the way you think about it. So I'm going to take this equation that I had and I'm going to plug in 10,000. Okay. And now it's just about solving it as an algebra equation. Okay, so how do we solve this like an algebra equation? I want to get x by itself. So the first step is not strange. I divide by the 10,000 to move it to the other side. And now I've got 5 equals e to the 0.0462x. Okay, so as an algebra equation, we have a new tool to be able to solve this. We need to get the x out of the exponent. Okay, to do that, we have to take ln of both sides. Taking ln of the right side is going to cancel the e and give us 0.0462x. Okay, that's because of that cancellation again. ln cancels with the exponent. On the left side, it's just taking ln of 5. I have to do whatever I do. I have to do both sides. That's how algebra works, right? So if I take ln of the right side, I've got to take ln of the left side. Okay. If you compare these two lines, you'll notice that I'm just saying the same old thing. I'm turning an exponential equation into a log equation, just like we did back in the first video on logs. I'm just using that definition. But I encourage you to think of it as taking ln of both sides, because it's a nice thing. It connects it with the previous algebra problems we've done, where you're always doing something to both sides of the equation. Okay, last step is easy. I divide by 0.0462. So now I have x equals ln of 5 over 0.0462, which is the answer if I don't have a calculator. But if I do have a calculator, let's put it in and check that we get x equal to 34.84. So it's saying that it takes that long to increase to 10,000. In other words, it takes that long to increase by a factor of 5. Okay, so here finally are the homework problems. Now, as usual, I would say this is a good time to pause and see how many of these you can do by hand. I'm going to give you some hints in just a second. Okay, so I'll let you pause and try as many of these out or get as far as you can in each of these, because I think that's the best way to start. Okay, so couple tips here. For the first one, if you're using the change of base formula, then you're going to turn it into either ln or standard log. I would practice turning it into ln because that's just the more common thing to do. All right. Now I did promise that one of these is possible without a calculator. I'm going to wait for class actually to answer that question. I want you to think about it for right now. If you need your calculator to do all of these, that's okay. All right. Second problem is very similar to the example on the previous slide. I'm asking it a little bit different because I'm asking how much does it take for the quantity to grow by a factor of 100. So the reasonable question is, well, what am I starting at? Okay. And my answer to that question is it doesn't matter what you're starting at. Now, if we go back to that previous slide, realize that I got to this equation where basically the only relevant information was that it was growing by a factor of 5. Okay. I mean, once I take the 10,000 and divide by 2,000, that's the only thing that's left. So what you could do is you could set up here e to the 3x, if r is 3, equals 100. If you need another way to think of it, you're thinking of it as you could think of it as growing from 1 to 100. And that would just make that coefficient 1 in front. Okay, for the last one, I would say you're using the change of base formula from the very first slide, turning it into a base E equation. So that means that the relative growth rate probably going to involve a natural log, and that's my hint for that last one. Okay, thanks. This is a little bit of a longer video. It's also our last video on logs before our first quiz on this. So I look forward to your questions in class and look forward to us getting lots of practice. I'll see you in class.